Welcome to this tutorial about sizing of flank modifications in the MESYS Shaft System Calculation. This tutorial shows how to determine optimal flank line modifications in the software for a simple two-stage gearbox. First, it is important that the stiffness of the gear body is taken into account by selecting one of the options for considering gear as stiffness. Either we increase the shaft diameter or we would use one of the 3D model options. In this case, we just stay with the increase of the shaft diameter. As graphics on the right side, the line load distributions of the two pairs is shown and the gap widths between the flanks. You see an uneven load distribution between the gears, which lead to a phase load factor, which would be maximum line load divided by average line load of 2.3 or around 2 for the second pair. Before starting the sizing of the modifications, we should have a look at the stiffness considered for the pairs. For the first gear pair, the gear mesh stiffness is set to the default value of 20 Newton per millimeter and micrometer, and this could be set to the stiffness based on ISO 6336 for the flank line modification C gamma beta. So this would now be a value of 11.5 Newton per millimeter per micron, and we do the same for the second case, for the second pair. Then we set the calculation option to A here on the bottom so that the software calculates the load distribution automatically, and because of the smaller stiffness, we already see that the phase load factor has been improved a little. I go to the first pair and to tooth flank modifications, and I see a gap width here of about 35 microns with a right flank contact. I use this value as a flank line slope modification for the first pair, and because of the direction, I know that I have to enter a negative value here. And now I get an improvement here, and the remaining gap is 2.5. The calculation is non-linear, so therefore I did not get exactly a horizontal line here. I enter 38 microns, and now I have an almost equal endpoints of the gap. The same is done for the second pair. I define a flank line slope modification of 18 microns, for example. I get a remaining 4 to 5 microns here, so I go here to 0.23 microns. Now this is also almost equal. The loading at the ends is slightly higher than in the middle, so I add some small crowning. Just 2 microns for the first pair and maybe 3 microns for the second one. The crowning modifications are very small, and that they would be only sufficient if there would not be any tolerances in the system. There are tolerances and manufacturing deviations and not an ideal geometry in reality, so let us consider flank line misalignments in addition. Under calculation with that plus button, you can define a mesh misalignment, FMA, as it's done in the strength calculation, and we can select a value of 10 microns here. We do that for the first gear pair and for the second gear pair. Click OK. Update the calculation. And now we see these dotted lines in the line load distribution, which show the line load under tolerances. So we see we get an edge loading for both of the gears, and therefore we increase the flank line modifications, the crowning, by around 5 microns, just a guess. half of the error. So I use 7 microns here for the first pair, and for the second pair I change this to 8, also adding 5 microns. So now we see a much better line load distribution for both of the pairs. This was the manual sizing of modifications, but this can also be automated. I disable the automatic calculation and open the parameter variation for optimization. I increase the window and the inputs are already prepared. So what do we do here? We minimize results based on some conditions. We want to minimize the phase load factor for the first and the second gear. And the inputs available for the variation are the crowning and slope modifications for the pinions. The gears will stay unmodified, but I could also do other distributions of the corrections. For the crowning, I specified a maximum value of 10 microns, and the flank line modification has a minimum of 0.1 and a maximum of 0.1 millimeter. The same for the second pair. The tolerance is set to 1 micron, that is sufficient. Now I run the calculation of this optimization, just clicking Calculate. After running the calculation, we see the results in the parameter list. So here we have the modifications for the flank, the crowning and the slope modification, and the same for the second gear, and we get a phase load factor of almost exactly 1. Clicking Save, this data is transferred to the main window. I click OK and I get this constant line load distribution. Now there was a small error in this optimization. I just used the phase load factor without considering the misalignment. So we see we get the result of 1 without misalignment, but with misalignment we have 1.323, and on this side we have 1.29. So we want to have an increased crowning. I go again into the parameter variation for optimization and I select different input values for the modification. I'm not choosing the phase load factor without misalignment, but the one with including misalignment, and the same for the second pair. Now I'm running the calculation again, clicking Calculate. Now, after the calculation is run, I could again check the results under the parameter list. We see a larger crowning here and a larger phase load factor, and I take over the results using Save. Running the calculation again now shows this load distribution with a maximum phase load factor of 1.14, including misalignments, and 1.17 for the second pair. This was a calculation for a single load case without load spectra. How do we do the calculation including load spectra? One option is we just consider some equivalent load, but that won't be the optimum for the whole load spectrum. So we could also do the whole process of sizing with the load spectrum. First, we define a load spectrum in the software. In this case, we defined a load spectrum. Before we had a moment load of 630. Now we have with 5% a higher load, and with 50% we have a lower load, and with 25% we have a quite low torque here at the bottom. The calculation could be run with the load spectrum, and we get a different line load distribution for every load case. So how can we determine the optimum load, the optimum modifications in that case. We go first to the gear connections and add that option for the calculation. We select that the phase load factor is passed to the gear calculation and the modifications are set to 0. So we just use the calculated phase load factor also for the calculation of safety factors. We do that for both cases. Then we go to the parameter variation again, parameter variation optimization. I increase the window again, and now we maximize the safety factors for the flank. The range for the modifications is the same as before. As start value, we can use the values we had before. Then the iteration of that optimization is a little bit faster, but we could also start with values of 0 here. So I click calculate again as before. After the calculation is done, we can have a look at the results using the parameter list, and clicking save, we can transfer the results to the main window and run the calculation again. Now we see this line load distribution here and here the gap width within the load spectrum. And if I open these lists for the result for the two gear pairs, I see the phase load factor for the individual cases, and we see that here for the maximum load it would be the smallest one, for the two highest load here for the maximum one, and for the lower loads we have a slightly higher phase load factor. The high loads has the largest impact on the safety factor in that case. The line load is shown here for each case, and we see that the maximum load is never at the edge but a little inside of the line load distribution.